Today, big graphs exist in various important applications, be it web, advertising, or social networks. Examples of a few such graphs are presented on the screen. These graphs allow the user to perform tasks such as target advertising, identify communities, and decipher the meaning of documents. This is possible by modeling the relations between products, users, and ideas. As the size and significance of graph data is growing, various new large-scale distributed graph parallel frameworks, such as GraphLab, Giraffe, and PowerGraph, have been developed. With each framework, a new programming abstraction is available. These abstractions allow the users to explain graph algorithms in a compact manner. They also explain the related runtime engine that can execute these algorithms efficiently on distributed and multi-core systems. Additionally, these frameworks abstract the issues of the large-scale distributed system design. Therefore, they are capable of simplifying the design, application, and implementation of the new sophisticated graph algorithms to large-scale, real-world graph problems. Let's look at a few limitations of the graph parallel system. Firstly, although the current graph parallel system frameworks have various common properties, each of them presents different graph computations. These computations are custom-made for a specific graph applications and algorithms family, or the original domain. Secondly, all these frameworks depend on different runtime. Therefore, it is tricky to create these programming abstractions. And finally, these frameworks cannot resolve the data extract, transform, load, or ETL issues and issues related to the process of deciphering and applying the computation results. The new graph parallel system frameworks, however, have built-in support available for interactive graph computation. Next, you will learn about GraphX, but before that, there's a quick pop quiz for you. GraphX is a graph computation system running in the framework of the data parallel system, which focuses on distributing the data across different nodes that operate on the data in parallel. It addresses the limitations posed by the graph parallel system. GraphX is more of a real-time processing framework for the data that can be represented in a graph form. GraphX extends the Resilient Distributed Dataset, or RDD abstraction, and hence introduces a new feature called Resilient Distributed Graph, or RDG. In addition, it simplifies the graph ETL and analysis process substantially by providing new operations for viewing, filtering, and transforming graphs. GraphX combines the benefits of graph parallel and data parallel systems as it efficiently expresses graph computations within the framework of the data parallel system. GraphX distributes graphs efficiently as tabular data structures by leveraging new ideas in their representations. It uses in-memory computation and fault tolerance by leveraging the improvements of the data flow systems. GraphX also simplifies the graph construction and transformation process by providing powerful new operations. With the use of these features, you can see that Spark is well suited for graph parallel algorithm. In the next topic, let's look at machine learning, which explores the study and construction of algorithms that can learn from and make predictions on data. This is the third topic of the lesson. In the previous topic, you were introduced to the graph parallel system. In this topic, you will learn about machine learning, its applications, and standard machine learning clustering algorithms like k-means. Let's first understand what machine learning is. It is a subfield of artificial intelligence that has empowered various smart applications. It deals with the construction and study of systems that can learn from data. For instance, machine learning can be used in medical diagnosis to answer a question, such as, "Is this cancer?" It can learn from data and help diagnose a patient as a sufferer or not. Another example is fraud detection, where machine learning can learn from data and provide an answer to a question, such as, "Is this credit card transaction fraudulent?" Therefore, the objective of machine learning is to let a computer predict something. An obvious scenario is to predict an event in future. Apart from this, it can also predict unknown things or events. This means that something that has not been programmed or inputted into it. In other words, computers act without being explicitly programmed. Machine learning can be seen as building blocks to make computers behave more intelligently. In 1959, Arthur Samuel defined machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. Later, in 1997, Tom Mitchell gave another definition that proved more useful for engineering purposes. A machine learning computer program is said to learn from experience, E, with respect to some class of tasks, T, and performance measure, P, if its performance at tasks in T as measured by P improves with experience, E. As data plays a big part in machine learning, it's important to understand and use the right terminology when talking about data. This will help you to understand machine learning algorithms in general. Let's begin with vector feature. It is an n-dimensional vector of numerical features that represent some object. It is a typical setting, which is provided by objects or data points collection. Each item in this collection is described by a number of features, such as categorical and continuous features. Samples are the items to process. Examples include a row in a database, a picture, or a document. Feature space refers to the collection of features that are used to characterize your data. In other words, feature space refers to the n dimensions where your variables live. If a feature vector is a vector length L, each data point can be considered being mapped to a d-dimensional vector space called the feature space. Labeled data is the data with known classification results. Once a labeled data set is obtained, you can apply machine learning models to the data so that the new, unlabeled data can be presented to the model. A likely label can be guessed or predicted for that piece of unlabeled data. Here is an example of features of two apples. One is red and the other is green. In machine learning, an object is used. In this example, the object is the apple. The features of the object, which is apple, include color, type, and shape. In the first instance, the color is red, the type is fruit, and the shape is round. In the second instance, there is a change in the feature description in the color of the apple, which is now green. As machine learning is related to data mining, it is a way to fine-tune a system with tunable parameters. It can also identify patterns that humans tend to overlook or are unable to find quickly among large amounts of data. As machine learning is transforming a wide variety of industries, it is helping companies make new discoveries and identify and remediate issues faster. Here are some interesting real-world applications of machine learning. Speech recognition. Machine learning has improved speech recognition systems. Machine learning uses automatic speech recognition, or ASR, as a large-scale, realistic application to rigorously test the effectiveness of a given technique. Effective web search. Machine learning techniques, such as naive Bayes, extract the categories or a broad range of problems from the user-entered query to enhance the result's quality. This is based on query logs to train the model. Recommendation systems. According to Wikipedia, recommendation systems are a subclass of information filtering system that seek to predict the rating or preference that a user would give to an item. Recommendation systems have been using machine learning algorithms to provide users with product or service recommendations. Here are some more applications of machine learning. Computer vision. Computer vision, which is an extension of AI and cognitive neuroscience, is the field of building computer algorithms to automatically understand the contents of images. By collecting a training dataset of images and hand-labeling each image appropriately, you can use ML algorithm to work out which patterns of pixels are relevant to your recognition task and which are nuisance factors. Information retrieval. Information retrieval systems provide access to millions of documents from which users can recover any one document by providing an appropriate description. Algorithms that mine documents are based on machine learning. These learning algorithms use examples, attributes, and values, which information retrieval systems can supply in abundance. Fraud detection. Machine learning aids financial leaders to understand their customer transactions better and to rapidly detect fraud. It helps in extracting and analyzing a variety of different data sources to identify anomalies in real time to stop fraudulent activities as they happen. You've learned what machine learning is and its applications. Now let's take a look at the role of machine learning in Spark. The scalable machine learning library of Spark is called MLlib, that contains general learning utilities and algorithms, including regression, collaborative filtering, classification, clustering, dimensionality reduction, and underlying optimization primitives. You will learn about some of them in the following screens. Spark excels at iterative computation, enabling MLlib to run fast. There are two types of API. Firstly, a primary API, which is the original spark.mllib. Secondly, there is a high-level API, which is the pipelines spark.ml. Spark 1.2 includes a package called spark.ml, which aims to provide a uniform set of high-level APIs that help users create and tune practical machine learning pipelines. You will learn about the steps followed in the general machine learning pipeline in the next screen. Here are the steps that are included in the general machine learning pipeline. The first step is data ingestion. When a user ingests data, it may not be in the correct form and may require some cleaning up and transformation, which is the second step. This data is an input for the machine learning algorithm. In the third step, the data goes through the model training. The next step is the model testing phase. In the final step, the model is then deployed and integrated. The model feedback then goes back to the users and reflects in the user behavior during data ingestion. In the next topic, you will learn about the 3 C's, or the techniques for exploiting data. In the previous topic, you learned about the applications of machine learning and the role of machine learning in Spark. In this topic, you will learn about the 3 techniques for exploiting data. Let's take a look at what these 3 techniques are. These include collaborative filtering, or recommendations, clustering, and classification. You will learn more about them in the subsequent screens. Let's begin with clustering. Clustering is an unsupervised learning problem with the objective to group the subsets of entities on the basis of some idea of similarity. It is generally used either as a hierarchical supervised learning pipeline component or for exploratory analysis. MLlib supports k-means clustering, which is a clustering algorithm. It clusters the data points into predefined number of clusters. You will learn more about k-means in the screens ahead. There are various other models of clustering that MLlib supports, such as Gaussian mixture, power iteration clustering, or PIC, latent dirichlet allocation, or LDA, and streaming k-means. Let's move on to classification. MLlib provides support to different regression analysis, binary classification, and multi-class classification methods. The table on the screen lists and explains the supported algorithms for every problem type. For binary classification, the supported methods include linear SVMs, logistic regression, decision trees, random forests, gradient-boosted trees, and naive Bayes. For multi-class classification, the supported methods include logistic regression, decision trees, random forests, and naive Bayes. For regression, the supported methods include linear least squares, lasso, ridge regression, decision trees, random forests, gradient boosted tree, and isotonic regression. Explanation of these methods is beyond the scope of this lesson. Let's take a look at two examples of classification. In the first example, you can see that the classification always gives a yes or no answer by creating routes. In case of a certain product, if the age of the customer is more than 20, and if the customer is female, it is likely that the customer will not buy the product. The second example is a sample random graph for classification. Collaborative filtering is generally used for recommender systems. The objective of these techniques is to complete a user term association matrix with entries that are missing. At present, MLlib provides support to model-based collaborative filtering. In this, products and users are explained through a small set of latent factors. These factors are usable for predicting the missing entries. The table lists the parameters that facilitate the implementation of MLlib. Let's begin with num blocks. It is defined as the number of blocks that are used for parallelizing computation. Rank is defined as the number of latent factors in the model. Iterations is defined as the number of iterations to run, while lambda defines the parameter of regularization in ALS. Implicit prefs explains what should be used out of the variant adapted for implicit feedback data or the explicit feedback ALS variant. Alpha is a parameter that is applicable to the implicit feedback ALS variant governing the baseline confidence in preference observation. Even though there are various techniques of exploiting data, which you have seen on the previous screens, there are some challenges in machine learning. Machine learning is highly computation-intensive and iterative. There are many traditional numerical processing systems that do not scale to large datasets, for example, MATLAB. Machine learning seems to be disrupting software engineering, challenging its impact on real-world applications. Now let's move on to k-means algorithm. You have learned that MLlib supports k-means clustering, which is one of the most commonly used clustering algorithms. K-means clusters the data points into predefined number of clusters. A parallelized variant of the k-means ++ method is also included, k-means pipeline. This table lists the parameters that facilitate the implementation of MLlib. K is the number of required clusters. Max iteration is the maximum number of iterations to run. Initialization mode specifies either random initialization or initialization via the k-means pipeline method. Runs is the number of times to run the k-means algorithm. Initialization steps determines the number of steps in the k-means pipeline algorithm. Epsilon determines the distance threshold within which you consider k-means to have converged. Shown here is the flowchart that illustrates how the k-means algorithm works. To begin with, the k-means clustering algorithm tries to split a given anonymous dataset, which contains no information as to class identity, into a fixed number, k, of clusters. Initially, the k number of centroids, which is a data point, imaginary or real, at the center of a cluster, are chosen. All centroids are unique, as each centroid is an existing data point in the given input dataset, picked randomly. For each data point, you need to calculate the absolute distance between the point and each of the k centroids. The data point then becomes part of the group of the centroid that matches the data point's minimum distance. Repeat steps 2 and 5 until the centroids no longer move. This produces a separation of the objects into groups from which the metric to be minimized can be calculated. Now, let's look at an example of k-means clustering. A telecommunications company wants to set up 3 towers to cover the entire population of a region and wants to understand how the customers are distributed. Here, you can see an anonymous dataset. The data needs to be clustered. The goal is to find the cluster of data points using k-means clustering. As the first step, choose k random points as starting centers. As you can see, 3 random points are chosen. These indicate the location where the 3 towers will be located. Secondly, find all points closest to each center. This is done by calculating the distance between the points. For example, the data points closest to the yellow point are clustered. Then find the center, or the mean, of each cluster. If the centers change, iterate again. You need to go back to step 2 to find all points that are closest to each center. These will look different compared to the points in step 2. Again, repeat the earlier step 3 of finding the center or mean of each cluster. If you find that the centers change again, you need to iterate again. Continue to do this until the centroids no longer move. You are finally done.
Hey, want to become an expert in big data? Then subscribe to the Simplilearn channel and click here to watch more such videos. To nerd up and get certified in big data, click here.